Let's remind ourselves what we mean by the expression 2 to the power of 3. That means we've taken the number 2 and we have multiplied it by itself 3 times. In an expression like this, we refer to that number 2 as the base, and we refer to this number 3 in various different ways. Sometimes we call it the power. Sometimes we call it the exponent. And sometimes we call it the index. There are a variety of laws that connect expressions like this, which we collectively call the index laws. Let's see how we can derive those laws. Firstly, if we have an expression like x squared and we multiply that by x cubed, well, x squared means x multiplied by x. We will have 2 of them. And we are multiplying that by x cubed, which means x times x times x. We will have 3 of them. How many x's have we got altogether? 1, 2, 3, 4, 5 of them. And it's clear that we got 5 of them because there were the 2 from here and the 3 from here. In general, we can see that if we have x to the power of m, where m is some positive whole number, multiplied by x to the power of n, where n is some other positive whole number, then we will have x to the power of m plus n. So we have our first index law for positive integer exponents. If our numbers m and n are positive integers, which is often described by saying they are inside this collection, this n with a double line, which means the collection of all positive integers, 1, 2, 3, and so on, then x to the m multiplied by x to the n is x to the m plus n. What would happen if we took, say, x to the 5 and divided that by x squared? Well, x to the 5 means x multiplied by x, multiplied by x, multiplied by x, multiplied by x 5 times. We're dividing that by x squared, in other words, x multiplied by x. Well, the usual rules of cancellation tell us we can cancel one of the x's from the top row with one of the x's from the bottom row. We can cancel another x from the top row with another x from the bottom row. And all we are now left with is x times x times x. In other words, x cubed. Now that 3 has come about because we have removed 2 of the things from the top to go with the 2 things from the bottom. In other words, we have subtracted the 2 from the bottom from the 5 on the top. So we have a general rule which tells us that if we have x to the power m divided by x to the power n, we will just get x to the m subtract n. Notice for this to make sense, m must be larger than n, because otherwise we would end up with m minus n being a negative number. At the moment we have no conception of what that might mean. So we have our second index law, which tells us that x to the m divided by x to the n is x to the m minus n, so long as m is bigger than n. We'll illustrate our next law by looking at some numbers again. Suppose we had 2 cubed to the power of 4. That means we have got one lot of 2 cubed multiplied by another lot of 2 cubed multiplied by another lot of 2 cubed multiplied by another lot of 2 cubed. But we already have an index law that tells us how to multiply, for example, the first 2 terms together. 2 cubed times 2 cubed would be 2 to the 3 plus 3. Similarly, the last 2 terms would also give us 2 to the 3 plus 3. And now we can apply the same law to both of these terms. We would have 2 to the 3 plus 3 for the first term, add 3 plus 3 from the second term. Altogether, we would have 2 to the 3 times 4 because we have got 4 lots of 3. This is an example of our general rule that says that if we have x to the power of m and then we raise all of that to the power of n, we have x to the power of m times n. This is our next index law. X to the m to the n is x to the m times n. Our next index law connects two variables. Let's look at an example. Suppose we have a variable x and a variable y, and we'll raise that to the power of 3. That means we have got one lot of x times y multiplied by another lot of x times y multiplied by another lot of x times y. Of course, x times y itself can be written as x times y. So we can rewrite that as x times y times x times y times x times y. When we are multiplying numbers together, it makes absolutely no difference which order we do that. So we could put those three x terms next to each other at the beginning and the three y terms next to each other at the end. So what do we have? X times x times x is x cubed. Y times y times y is y cubed. What we have here is an example of our general rule that if we have xy raised to the power of n, that is the same thing as x to the power of n times y to the power of n. Formally, our next index law is that xy to the n is the same as x to the n, y to the n. Let's look at some examples which put these laws into practice. Use index laws to simplify the following expressions. This is also a good opportunity to clarify what we mean by an expression. An expression is just a collection of terms which we have to consider in its own right. It's not part of an equation. There is no equal sign that tells us what all this comes to. We just have to take the terms we're given and perhaps see if we can write them in a slightly nicer way. So in part A, we have to say, what is a nicer way of writing x to the 4 multiplied by x to the 5? Our first index law tells us that when we have x to one power multiplied by x to another power, we have to add the powers together. So it would be much nicer to write that as a single term, x to the 9. In part B, we can apply the same law to 4x cubed multiplied by 7x to the 6. It might help us to realize that 4x cubed, for example, means 4 times x cubed. The power 3 is only attached to the x, not to the 4. If it was attached to the 4, the 4x would have to be in brackets before we cubed it. Similarly, the 7x to the 6 means 7 times x to the 6. So it would be better to put the 4 and the 7 together at the beginning before we then multiply x to the 3 by x to the 6. 4 times 7 is 28, and x to the 3 times x to the 6 is x to the 3 plus 6, x to the 9. In part C, we have x to the 9 divided by x squared. So our rules of indices tell us that this will be x to the 9 subtract 2. This comes to x to the 7. In part D, we have 12 x to the 7 divided by 3 x to the 6. We must again realize that 12x to the 7 means 12 lots of x to the 7. The power 7 is only connected to the x, not to the 12. Similarly, 3x to the 6 means 3 lots of x to the 6. So we can split this into two fractions. This is the same thing as 12 divided by 3 multiplied by x to the 7 divided by x to the 6. 12 divided by 3 is 4, and x to the 7 divided by x to the 6 is the same as x to the 7 subtract 6, which is 1, so we have 4 times x to the 1. And of course we don't bother writing the x to the 1, that just means we have a single x, so we would just write that as 4x. Some more expressions to simplify using index laws. In part A, we have to simplify x to the 4 to the power of 3, and we have an index law that tells us that when we do this, we have x to the power of 4 times 3, so that can be written much more concisely as x to the 12. In part B, we have to simplify 3x squareds to the power of 4. Using our final index law, we can write that as 3 to the power of 4 multiplied by x squared to the power of 4. 3 to the power of 4 is 81. X squared to the power of 4 is x to the 8. Because a power to a power, we have an index law which says we multiply those two things together. Incidentally, knowing that 3 to the power 4 is 81 is one of several things which is very nice to know. Throughout the A-level course, you don't really need to know an awful lot of mental arithmetic. You always have access to a calculator. But recognizing low powers of 2, 3, 4 and 5, that's probably about as far as we would need to go, are very useful to help you spot shortcuts in some questions. You should also be able to recognize square numbers at least up to 12, and a little bit further than that is nice as well. In part C, we have to simplify x times y to the power of 11, and what more can we say than that is the same thing as x to the 11 times y to the 11. And finally in part D, 2 lots of x times y to the power of 5. Well, one way we could do this would be to regard the thing we are raising to the power of 5 as the product of 2x and y. So therefore we can use our index law to write 2x to the power of 5 times y to the power of 5. Then we could use the law again to split the 2x to the 5 into 2 to the 5, x to the 5. We've still got that y to the 5. So our final answer would be 32, being 2 to the 5, times x to the 5, times y to the 5. But you may have noticed that we could have got this directly if we had started with 2xy to the 5, and just immediately split that into 3 pieces, 2 to the 5, x to the 5, y to the 5. We could have immediately gone to our 32, x to the 5, y to the 5. This is an example of a rule which can be extended from just 2 terms to many terms. And looking back at the index laws we have developed, this will be true for the first, third and fourth. The second one, because it deals with division, would require a lot more thought and care if we're going to extend that to sequences of divisions, and that would be best done on a case-by-case basis. We may have to do some expanding of brackets in some cases. In part A, we have to simplify 5x cubed times 3x to the 4 subtract 2. So expanding the brackets, 5x cubed times 3 times x to the 4, or 5 times 3 is 15, and we have x to the 3 multiplied by x to the 4. We'll simplify that in a moment. Then we have to subtract 5x cubed times 2. 5 times 2 is 10 times x cubed. And finally, we can write that as 15 times x to the 3 plus 4 is 7, subtract 10x cubed. In part B, there's quite a lot of expanding to do. 7x into 2 subtract 3x squared. And then we have to subtract x cubed into 4x plus 1. Expanding the first bracket, 7x times 2 is 14x. 7x times negative 3x squared, 3 sevens are 21, so we're subtracting 21. X times x squared is x cubed. Now we have to subtract x cubed times 4x, so that will be subtracting 4x to the 4s. We also have to subtract x cubed times 1, in other words, subtract x cubed. Finally, tidying all the pieces up, how many x's do we have? 14 x's. How many x cubeds? Negative 21, and then we need to take another one away, subtract 22 x cubeds, and we have negative 4x to the 4. In some situations we may have to deal with quotients, one thing divided by another. So in part A, when we have x to the 5 plus x to the 9 divided by x squared, the best thing we could do is to split that into two fractions, x to the 5 over x squared and x to the 9 over x squared, because our division stroke subtraction law tells us that x to the 5 divided by x squared is x to the 5 subtract 2, which is x cubed, and that x to the 9 divided by x squared is x to the 9 subtract 2, which is 7. Part B is very similar. If we start off with 16x to the 7s, subtract 8x to the 4s, divided by 4x cubed, we should again begin by splitting this into two fractions. 16x to the 7s divided by 4x cubed, subtract 8x to the 4 divided by 4x cubed, and it may be best to split each of the fractions into two pieces, one involving the numbers and one involving the powers of x. So in the first case we have 16 over 4, subtract x to the 7 over x cubed. In the second part we'll have 8 over 4 multiplied by x to the 4 over x cubed. For the first of these terms, 16 over 4 is 4. What have we got 4 lots of? X to the 7 over x cubed, which will be x to the 7 subtract 3. That will be x to the power 4. Then what do we have to take away? 8 over 4 is 2. What have we got 2 lots of? X to the 4 divided by x cubed, x to the 4 subtract 3, x to the 1, or just x.